Very much, and thank you to the organizers of this symposium. My name is Robin Armstrong, and I'm a PhD candidate in applied mathematics at Cornell University. Today, I'm going to be telling you about an ensemble Kalman filtering technique that I've been developing, which uses quadrature to incorporate model space localization more efficiently. And everything in this talk is joint work with Ian Grooms, Associate Professor of Applied Math at CU Boulder, and Chris Snyder, a Senior Scientist at the NSF-NCAR Mesoscale and Microscale Meteorology Lab. So just to review some notation first, my state vector is going to be denoted x. So x sub f is the forecast, x sub a is the analysis. My data is going to be denoted y, and my forward operator is going to be h. I'm going to use mu's to denote the ensemble means and sigmas to denote the ensemble covariances. I'm also going to be making the standard assumption in Kalman filtering, which is that the state variable and the data have a jointly Gaussian prior distribution. And as I'm sure you're all aware, this assumption gives us Kalman's equations for the analysis distribution. For the purposes of this talk, what I want to point out about Kalman's equations is that they relate the forecast distribution to the analysis distribution using this matrix K, the Kalman gain, that involves an inverse. And the reason I'm pointing this out is that in the setting I care about, X is a state variable representing the state of a model for the atmosphere, and Y is a collection of satellite radiance measurements, meaning X and Y are both extremely high dimensional, as are the matrices appearing inside the Kalman gain. So in this talk, I'm going to be very concerned with the efficiency of operations, for example, matrix inverses, that are necessary to evaluate the Kalman update. I'm going to be looking at ensemble Kalman filters. So that is algorithms which transform a finite sample from the prior into a finite sample from the posterior. There are, of course, many such algorithms for doing this, and the very first Kalman filter did this by simply transforming each ensemble member as if it were the mean of the forecast distribution. This is very convenient computationally. We only need to solve a linear system for each ensemble member, but it actually does not give us the right distribution on the other side because it systematically undercounts observation error. So one of the classical solutions for getting around this is to add stochastic noise to the observation vector. This gives us the classic stochastic ensemble Kalman filtering algorithm. But another workaround, which I'm going to be more focused on in this talk, is the ensemble square root filter, or the deterministic ensemble Kalman filter. Here, the idea is that we're going to first recenter the mean of the ensemble and then separately rescale the perturbations of the ensemble from the mean. Now, in order to rescale the perturbations, we need to multiply them by this matrix G called the modified Kalman gain matrix. And what I want to point out to you is that the modified Kalman gain is almost exactly like the Kalman gain, except it includes this extra contribution to the observation error in the form of this matrix square root. And when our data vector is extremely high dimensional, evaluating this square root poses a computational challenge. Now, the situation would not be so difficult if our forecast distribution were just the pure empirical distribution of the forecast ensemble, because then the forecast covariance matrix would already be in low-rank form, and we could do all of our calculations in ensemble space, making that square root much easier. Unfortunately, the pure ensemble covariance of the forecast ensemble is generally too undersampled and noisy for it to be useful for data assimilation, meaning we need to apply some kind of localization. And in this talk, I'm focusing on model space localization, which is to say, doing an element-wise product between the forecast ensemble covariance and a tapering matrix L. This localized estimate for the ensemble is much less noisy, but it is also full rank, meaning it's difficult to compute with because it does not have an ensemble representation. It turns out that it is fairly easy to do matrix vector products with this localized ensemble covariance. And so because of this, we can run Krylov methods and solve linear systems. This is an already known fact. I first saw it in a paper in the 2019 paper of Farchi and Baquet. But even though we can solve linear systems, the square root that we need in the modified Kalman gain is more difficult. One of the classical solutions to this is ensemble modulation. The idea here is that we can construct a larger ensemble of synthetic forecast perturbations whose empirical covariance retains some of the effects of localization. So mathematically, this is essentially just taking a low-rank factorization of the localized forecast covariance. There are many ways to construct the modulated ensemble. A classical technique from Bishop et al. Is to use a spectral decomposition of L. Farchi and Bouquet did it using randomized singular value decomposition. Whatever technique you use to generate the modulated ensemble, it's only going to work well if the localized forecast covariance has a fast singular value decay to begin with, because the singular value spectrum imposes a fundamental limit on what kind of accuracy you can get from any low-rank approximation. Later in this talk, I'm going to be comparing ensemble modulation against a method that I'm going to show you in a minute. And when I do this comparison, I'm going to want to reference to a measure of complexity of the overall algorithm. For the ensemble modulation as a measure of complexity, I'm going to be using this parameter k, which is the size of the modulated ensemble divided by the size of the original ensemble. Now, what my collaborators and I have been working on is a method for doing the perturbation update which incorporates model space localization, but which avoids the square root, and therefore avoids the need to modulate the ensemble. Now, to motivate this method, I want to recap a little bit about the stochastic ENKF. Remember that this method updates each ensemble member as if it were the mean of the forecast, distribution, but to counteract ensemble collapse, it adds stochastic noise, denoted here as xi, to the observation vector. Now, this is quite attractive computationally because it means that we only need to do a linear system solve for each ensemble member. Our algorithm works quite similarly, except that instead of adding stochastic noise to the observation vector, we deterministically inflate the observation error covariance matrix by this positive value S. This means that we're essentially updating each ensemble member as if it were the mean, but we're using an inflated Kalman gain matrix, which I denote as K of S. Now, for any particular value of S, this procedure does not yield an analysis ensemble whose covariance matches what would be required from Kalman's equations. However, one of the fundamental results we proved is that if you apply this procedure only to the perturbations of the forecast ensemble and you average over an appropriate range of inflation values, then you actually do get an analysis ensemble whose mean and covariance agree exactly with Kalman's equations. This is the basis for the algorithm I'm going to show you today, which updates the ensemble by discretizing this integral that's averaging over different inflation values. Now, if you're paying very close attention, you'll notice that the integral we want to evaluate is weighted by this function p of s, which is actually extremely slowly decaying. P of s scales about like s to the minus 3/2, so it does not even have a first moment. Therefore, in order to be able to discretize this integral practically, we need to reweight it in order to deal with this slow decay. This theorem that you can see on this slide right here gives a very general procedure for reweighting the integral in a manner that depends on the spectrum of the forecast covariance matrix in observation space, normalized by observation error. The essence of the theorem is that any quadrature rule for computing the inverse square root of a scalar can be adapted to a quadrature rule for computing the Kalman update according to this integral-based algorithm. And this leads to the algorithm that I want to present to you today, which my collaborators and I have been working on. We call this info ESRF, which stands for integral form ensemble square root filter. And the essence of the algorithm is to discretize the integral representation of the Kalman filter perturbation update that I've shown you on the previous slide. So concretely, the way it looks is that we start with our ensemble of forecast perturbations. We create Q separate copies of this ensemble, where Q is the number of nodes that we're going to use in our discretization of the integral. Now, for each of these Q separate copies, we perform a perturbation update based on the standard Kalman gain matrix, but with an inflated observation error covariance matrix, and the inflation value depends on the particular quadrature point we're using. In order to do this update, we simply need to solve a linear system to apply the inverse in the standard common gain, and we do this using preconditioned conjugate gradients. This leaves us with Q sets of analysis perturbations, which we then average together, weighting according to the quadrature rule. And after this averaging procedure, we're left with our final analysis ensemble. I'm going to be comparing this method in a few slides to modulation, and so I need a measure of complexity to compare against. Whereas in modulation, we were looking at the size of the overall modulated ensemble. Here, as a notion of complexity, I'm going to be looking at the size of the ensemble multiplied by the number of quadrature points that we're using. The reasoning here being that this is the overall number of vectors that we need to apply a standard common gain to throughout the course of this algorithm. I'm going to show you two test cases with this algorithm. The first is a multi-layer Lorenz type system that comes from Farchi and Bouquet in their 2019 paper in FAMS. So this consists of 32 coupled layers of a 40 variable Lorenz 96 system. The forcing decreases linearly from F equals 8 at the bottom to 4 at the top. We use measurements that correspond to 5 weighted vertical integrals for every fifth column, although this is a discrete system. So when I say integral here, I really mean sum. And every observation is perturbed with IID Gaussian noise, whose variance is about 1% of the climatological variance for that observation. This observing system comes from Farchi and Bouquet as well. For localization, we're using the Gaspari-Cohn model space localization function in both the horizontal and the vertical. We use equal horizontal and vertical localization radii that were tuned for a cycled data assimilation experiment based on a GETKF where the modified common gain is evaluated exactly, so no modulation, no approximation. In the experiment that I'm going to show you, it's a cycled data assimilation experiment with 5,000 forecast assimilation cycles, a time of 0.05 between each one. And I'm going to measure the average forecast MSE and spread over the last 4,000 cycles. Here are the results. Let's start by focusing on the left-hand panel. On the horizontal axis is a measure of overall complexity. So for the GETKF methods with modulation, there's one by modulation from a modulation product, the other by modulation through a randomized SVD. For these modulation methods, the horizontal axis is the ratio of the modulated ensemble size to the overall ensemble size. For info ESRF, the integral-based filter that I have been discussing today, there is no modulated ensemble, but there is a notion of enlarging the ensemble by creating Q copies of it through the quadrature. And so for info ESRF, the horizontal axis is the quadrature size. The vertical axis is the average forecast mean squared error averaged over the last 4,000 cycles of this 5,000 cycled experiment. And there's a dotted line here showing a system, an ensemble with no data assimilation at all for reference. Now, the important things to notice here are that the modulation methods become more accurate as the ratio of the modulated ensemble to the original ensemble size grows larger. This is what we would expect, as using a larger modulated ensemble lets us approximate the covariance more accurately. Modulation with a modulation product is generally not doing as well as modulation with a randomized SVD. This also makes sense because the randomized SVD generally gives us a more optimal approximation to the forecast covariance. But what I really want to point out here is that the integral filter is having lower forecast errors than all of the modulation-based filters. The reason for this is that the integral-based filter simply needs to solve a linear system for every ensemble member and at every quadrature point. And it can do this via a Krylov subspace method that only needs to access the forecast covariance as a linear operator. You may remember from a few slides ago that this linear operator access can be done exactly with no approximation at all, even with a localized forecast covariance. So essentially, the integral filter is using a more controlled approximation that does not require us to introduce any errors to the forecast covariance itself. Moving to the right-hand panel, the horizontal axis is the same measure of complexity. The vertical axis is the average ratio of the forecast mean squared error to the forecast variance. And what I want to point out to you is that of all the filters we're looking at, the integral-based filter has the ratio closest to 1, which means that the variance of its ensemble that it's giving us is the most representative of the actual error in the forecast. You may also notice that in both of these experiments, the accuracy of the interval-based filter does not depend strongly on the quadrature size. We interpret this to mean that even for a very small quadrature size, k equals 4 at the leftmost ends of these plots, already that quadrature is providing an accurate enough approximation that any remaining errors have to do with the Gaussianity and linearity assumptions in the Kalman filter, and these errors cannot be eliminated by making more accurate approximations to the forecast covariance. The second case that I want to show you is very much work in progress, but I think it's exciting. We've been working to implement this algorithm in MPAS-JEDI, MPAS being the atmospheric model for prediction across scales, JEDI being the joint effort for data assimilation integration. The test case I'm showing you here uses a 20-member background ensemble. These members come from the GEFS reanalysis. The background covariance is coming from JEDI's Sabre ensemble covariance model with bump notcast localization. The observation I'm going to assimilate is a single pressure observation. The map that you see here shows a large collection of pressure observations. I'm going to be assimilating this one taken over Italy. And for the implementation, remember that our integral filter simply needs to apply standard Kalman gains with inflated observation error covariances. And we apply these Kalman gains using MPAS-JEDI's 3D NVAR executable using only one outer loop. This test case is quite preliminary, but here are the results. On the left-hand plot is the change in ensemble variance from forecast to analysis for an EDA 3D NVAR system with perturbed observations. On the right-hand plot is the same thing, change in ensemble variance from forecast to analysis using our integral form filter, which does not use perturbations of the observations, but instead uses these inflated Kalman gain matrices averaging over inflation values. We find this result to be encouraging because it shows us that the reductions in ensemble variance being computed by our integral form filter in MPAS-JEDI are quite close to the reductions in variance that we see from standard, well-developed and tested filters in the JEDI framework. And so that gives us some encouragement that our method's doing the right thing. So in summary, we've demonstrated an ensemble square root filter which updates perturbations by discretizing an integral form of the Kalman filter update equations. This lets us avoid explicitly evaluating a matrix square root, and because of this, it eliminates the need to approximate the localized forecast covariance with modulation. If you're interested in learning more, I'm happy to take questions, and I also encourage you to read our preprint, which is recently out on arXiv. Thank you very much.
Okay, great. Thank you very much, Robin. Okay, so any questions on the OPAD? Just wait a little time, see if any questions come through. Okay, so I think because we are a little over time, I think we should probably move on, and there's no questions. So if anyone in the audience does have a question for Robin, if you could use the OPAD to please write your question, and Robin, you could answer them on the OPAD later on. That's okay.
Sounds good. Thank you.
Yeah, great. Okay.